Today we're going to be learning about Euler's method, which is a method that we can use to approximate solutions numerically to differential equations. I know lots of times we want to have exact solutions, but often that's not possible, either because we don't know how to solve the differential equation, or maybe it's possible for us to solve it, well, we don't really need all of the accuracy of the exact solution, and an approximation would be acceptable. So this is going to be sort of an algorithm method, a numerical method that we can use to approximate solutions to differential equations. But before I can really get into Euler's method and how to do it, there are two things that I need to make sure that we're comfortable with. The first of them, a slope field, I think is something that you guys have learned about before, and the second, an isocline, might be something that you're not as familiar with. So a slope field is just what I've written there. It's an illustration of the slopes associated with a differential equation at several points. So you guys may at some point remember that you might have been given a graph that has a bunch of points on it, and you were asked to complete a slope field. And as I'm doing this one, I'm like making it as bad as possible. Because the method that people generally use, well, I think that we often use in high school for finding slope fields, is for you to take your differential equation. Maybe you have a differential equation dy dx equals y plus x. And to draw the slope field for this, you would go through and pick a point like 1, 1, and then plug in 1 and 1, find out that that's 2, and then come back over here to your slope field and do your best to draw a little slope of 2, and then you go on to the next one. You go to the point 2, 1, and you plug that in and find that's a slope of 3, and you try to make something with a slope of 3. And it's all it takes a long time to do it. There is another method that you can use to do these, and that uses something called isoclines. So if you haven't heard of isoclines before, an isocline is, it's sort of two words, isocline. So iso means same, and cline comes from the same root as like incline or slope or increase. So an isocline is just a line or a curve that runs through a slope field at which every point has the same slope. So for instance, if we knew that there was one particular curve that went through a slope field where all of the points on that curve had the same slope, we could really quickly fill in a whole bunch of things on a slope field. To get a sense for how to use isoclines to help us build slope fields, we'll look at an example. So here you're being asked to consider the differential equation dy dx equals x plus y. Part A, we're going to be asked to find the isocline corresponding to a slope of 0. So what this effectively says is it's basically asking us, can we find the isocline, can we find the curve through the slope field where every one of the points in that curve has a slope of 0? It's actually really, really easy to do. If we look back at the differential equation, my differential equation says that my slope is going to be equal to x plus y. So if I just do 0 equals x plus y, I find that along the line y equals negative x, all of those slopes are going to be 0. So what that means for us is that if you imagine that I'm trying to construct my slope field, the line y equals x would be, y equals negative x would be right here. And so what this means, it means that every point along this thing, the slope for my slope field is going to be 0, which means I can go back through here and put in a bunch of 0 slopes that are following right along this line y equals negative x. Okay? And so rather than for me having to plug in a bunch of points, I'm finding that every single point along that line, along that isocline, is going to have a slope of 0. So similarly, we can go back for part B of this and say, all right, well, find the isocline corresponding to a slope of 1. So that would be 1 equals x plus y, which would mean that y is negative x plus 1. And so, hopefully we're sort of seeing where this is going. I know what the line y equals negative x plus 1 should look like. It's just going to be the same line shifted up by 1, right? So this here, along that line, I'm going to have a bunch of slopes of 1. Okay. Part C of this question is really just asking us now to find the general equation of the isoclines. Well, the general equation of those isoclines would be C, because for whatever slope we might be thinking of, we were thinking of 0 and 1 in the first ones, and now we're going to think generally. This, by the way, is sort of different from the constant of integration. This is just a constant that we're using. So C equals x plus y. So the general form of this thing would be y equals negative x plus c. which like if you look a little bit more deeply, this basically tells us that whatever the y-intercept of the line with slope negative x is, that's what those slopes will be. So it means that I can go back through this thing now and say, all right, well, when I'm up here at a y-intercept of 2, along this line, I'm going to have slopes of 2. Down here, when the y-intercept was negative 1, that means I'm going to have a slope of negative 1 for those ones. So negative 1, negative 1, negative 1, negative 1. And so do you see how you can really quickly construct a slope field that gives you way more points than you might have had before? I'm going to sort of stop at that point just to save ourselves some time here. But I hope you see how isoclines can really help you to come up more quickly with a slope field. The last thing that I'll say here is, remember that one of the points of a slope field, one of the points of a slope field is that if we pick some starting point like 0, 0, you can kind of imagine what the solution curve would look like as you go through here. It goes out sort of horizontally, and then it starts curving upward and going like this. As we go backward, it looks like it's kind of just heading toward this line with slope negative 1. That's sort of the purpose of slope fields, to give us a sense for what these things look like. And Euler's method is going to take that and make it a little bit more formal. So what Euler's method is effectively going to let us do is it's going to let us pick a starting point and then sort of choose a step length that we're going to use to sort of walk through this slope field, right? So in this left picture, there's this idea that if we use the step length of 1, if I were to start out at this point right here and find the slope according to the slope field and then follow that slope for 1 unit, I'd get to a new point. From that new point, I could find the new slope, and I could follow that slope for 1 unit. And then from there, I could find the new slope on the slope field and follow that one for a step of 1 unit. And you might have noticed that this step seems smaller than this step, but I keep saying that it's a step length of 1. When I say a step length of 1, what I'm talking about is I'm talking about movement on the x-axis. So I went from, this might be negative 2. I went from negative 2 over to negative 1. And then I went from negative 1 over to 0. And then I went from 0 over to 1. So each of this, when I say the steps are the same, I'm talking about the x step. Right here, there was a huge y step. That's okay. This is part of Euler's method. Okay. We can make Euler's method better by taking smaller steps, right? Over here, we do the same thing, but each time I'm only using that slope for a half before I recheck what the new slope is and follow it for a half, and recheck the new slope and follow it for a half, and recheck. So the smaller I make these steps, the more accurate of an approximation I'm going to get, but of course it's going to take longer. That, of course, is sort of one of the trade-offs that we have in algorithms and things like that when we're working with accuracy. So one more thing I'll say is, because this is an algorithm, and you guys will see the steps in just a moment, it's very, very, very easy to translate this into something that you can code, whether you sort of code that on your calculator or whether you build it in an Excel spreadsheet. This is something that you need to know how to do conceptually, but once you've got that, it's definitely something that you can sort of put to code. Hopefully, really briefly here, I want to go through what sort of the step-by-step guide is on Euler's method algorithm. So the first step is you're going to want a table. There's going to be a lot of information here, and not recording it is kind of a recipe for disaster. Also, often on exams, you're going to end up getting part of the credit coming from you filling in the table and showing that work along the way. So in your table, you'll want to have columns for x values, y values, the slope, and then dy, which is going to represent that change in y, the movement up and down. Okay? And then steps 2 through 6 are basically going to be our algorithm, the thing that we're going to repeat. So you'll start by entering your initial point into the x and y columns. You'll take those x and y values and plug them into the differential equation to find out what the slope is at that point, right? Once you have that slope, you're going to multiply that by the step size, which is basically dx, to find out what the change in y is going to be. By the way, to give you a sense for why that makes sense, if you think about the fact that you have a dy dx, a rise over run, and you multiply by dx, sort of the change in x, I know these don't precisely cancel out, but there's this idea that when you multiply a rate of change by the change in x, you're going to get out the change in y. Okay? So, we've got this change in y. We have this idea of how much if I follow that slope line, how much that y value is going to change. And so the next thing we do is we start setting up to repeat this process. You'll then take your step size and add it to the current x value and put that in the next line of your chart. And then you'll add this change in y that you just found to your current y value, and you use that to find the next y value. At this point, you have your new x and your new y, and you go back up here to step 2 to repeat the process again. And you just keep doing this over and over and over again until you get to the point that you want to end on. The last thing I'll say here is because this is a numerical algorithm, something where you're going to get approximation and plug it in and work through it again, and get an approximation, plug it in and work again, even if a problem says, hey, you might only need 3 significant figures for your answer, you'll really want to make sure you use as much accuracy as you can as you're going along. So store values, recall values, like please don't get a number from your calculator and type that number in again. It's really important that you sort of store as much accuracy as you possibly can. All right, so let's go ahead and get through this problem. When you're working with Euler's method, I mean, as far as I've always seen them, you're always given a step length in a problem. Now, if you're on your own doing math, you get to pick the step length. But often in problems, you'll be given a step length. You'll be given a differential equation. Okay? You'll be given an initial condition, right? It was given that y was 1 when x is 0, and you'll be told sort of where to stop, what that value is that you're looking to stop at. So I mentioned on the previous slide that when we do these problems, we really want to set up sort of a table for ourselves. We want to be tracking what's our x value, what's our y value, what's our dy dx, and then what's our change in y. Okay, and so these are the things we're going to be tracking, right? So in the beginning of the problem, we're beginning by indicating that my initial x value is 0, my y value is 1, and we remember we're going to be stopping when we get to an x value of 1. The other thing that we can do, actually right off the bat, is because the step length is 0.25, we know that our next x value is going to be 0.25, the next one will be 0.5, the next will be 0.75, and the final one will be 1, and it's worth noting that as soon as we get down this far, this is where your answer is going to be. Right? You actually don't need to fill out the rest of that row, because at this point we will have hit the end point of the process. Okay? So I'm going to go ahead and go through the first step here with you guys, and then after that I hope that you'll give these a try on your own and get a chance to do it. So I'm going to be taking this x value and this y value and plugging them into the differential equation. So when I plug in 0 for x and 1 for y, it looks like I'm going to get negative 1 plus 2, which is going to be 1. So my dy dx value here is 1. For dy, I'm going to take that dy dx value 1, multiply it by the change in x, my step size, and find out that that's 0.25. So I get my dy is also 0.25. Now, for right now, it looks like x is going up by 0.25, y is also going up by 0.25. That will not always be the case. These values are definitely going to change as we're going along. So for this y value here, I'm supposed to take the 1 that I had before and add that to it. I now have 1.25. Okay, so pause the video for a moment. Make sure that you have a sense for what it is that you're supposed to do next. So the idea here is now I'm supposed to take these x and y values, plug them back in up here, get a new dy dx, which I'll multiply by the step size to get a new dy, and then add that here. And I'm just going to keep repeating that over and over and over again until I hit the end of this problem. So, pause the video, go through at least the next one step, make sure that you can get that before you go on and do the rest of the steps. It can definitely be frustrating to do this multiple times and then find out you made a mistake somewhere in the middle. So as you guys saw when you tried this out, you should have found that these numbers got messy pretty quickly. The dy dx value that we had at this point was 0.6875, and then when I multiplied that by 0.25, I'm going to get 0.171875. This is one of those things where it takes us a lot of time to write down all of these digits. I don't know that it's necessary that we have every bit of accuracy in our table, but what's very important is that when I take this value and add it to y to get this, even if I don't write the full value here, I'm going to store and use that when I move forward to find what dy dx is. So I'm going to pause the video here, and in just a couple seconds I'm going to pop up all the values here so that you can check those things and you'll be able to see what your answer is at the end. So after using Euler's method 4 times, sort of, 4 steps, steps through the slope field, we find that our approximation to the value of y when x equals 1 will be this. So that's that. If you were doing this problem in real life and needed more accuracy than that, what you would do is you would use a step length that's smaller than 0.25. You could use a step length of 0.1 or 0.01. Those would take you 10 or 100 repetitions of this algorithm, which would be horrible to do by hand, but with a computer is something that we can do really, really, really quickly. So hope all that made sense, and best of luck as you try these problems on your own.